Welcome back to this course on polymer chemistry, and in this lecture we are going to begin our discussion on polymer stereochemistry and then followed by a discussion on coordination polymerization. Now, we will start with our discussion on constitutional or structural isomers and then go into polymerization of conjugated dienes, which will give some insight about geometric isomerization of polymers, and then go into different types of tacticity possible in polymers, how to analyze those tacticity, and how we can control or we can preferentially synthesize a polymer with desired tacticity. And then we will talk about Ziegler-Natta polymerization, and then briefly talk about metallurgical polymerization and give some example of commercial coordination polymers. Now, this will cover in this lecture and the next lecture, which is lecture number 24. Now, let us start with our discussion on constitutional isomers, which sometimes also called structural isomers. Now, let us consider a polymer having repeat unit molecular formula of C2H4O. Now, that is the formula of the polymer repeat unit. Now, what are the polymer possible with this molecular formula? We can write something like this, which is PEO, polyethylene oxide, or we can think of a polymer like this, which is polyacetaldehyde. Or we can also think something like this, which all of these three we now written, they have all same molecular formula. This is polyvinyl alcohol. So, basically these are the examples of constitutional or structural isomers as we know from our knowledge, basic organic chemistry knowledge. Similarly, we can write other structural or constitutional isomers, like we can write polyvinyl acetate, which is having structure now. This is the structure of polyvinyl acetate. Now, you think polymethyl acrylate. Now, polymethyl acrylate, you can yourself write down the structure and then find out that this has the same molecular formula as polymethyl acrylate. We can give other examples like PMMA, polymethyl methacrylate, and polyethyl acrylate, polymethyl methacrylate, polyethyl acrylate. They are all examples of structural isomers. Now, we can also have other types of examples. For examples, we know that polyamide, we can have polyamides from diol plus diacid. For example, we have say from hexane diol and adipic acid, we form polyhexamethylene adipate. We form this polyester. Now, we can get the same polyester by ring opening polymerization of cyclic lactones. We also can form similar condensation polymers like polyamides. Now, in case instead of diol, if you use hexane diamine and use that adipic acid, we will get polyhexamethylene adipamide. Now, this same polyamide having same molecular structure, molecular formula, we can get it from ring opening polymerization of caprolactam. So, basically these two are again examples of structural isomers in case of polymer chemistry. Now, we also have seen during our discussion of chain polymerization synthesis that always it is the head tail arrangement when polymer chain propagates, it is a head tail arrangements always preferred almost exclusively over a arrangement like head. Now, if you can form polymers having head to tail and head to head structure, then those will also give same molecular formula, but we know that we always get head to tail polymers in case of chain polymerization. Now, we can have, let us talk about the polymerization of conjugated diene. This will give us idea about geometric isomerization. Now, let us consider the simplest of the dienes which are 1,3-butadiene. Now, you can have substituted 1,3-butadiene as well. Now, we can write general formula like this, or we can write, if it is a substituted, we can write a R instead of H, and we can write this. If R is CH3, then it is isoprene. If R is chloride, then it is chloroprene. Now, how when you do a chain polymerization on this type of monomers, how can you imagine what are the possible polymers these monomers are forming? For example, let us take example of this general structure and see how we can think of different polymers getting produced from these general 1,3-butadiene type monomers. Now, let us take out the basic modes by which this monomer can polymerize. If this is a 1:2 addition, then you will get a polymer like this. If it is a 3,4 addition, you can recall the molecule, this is 1, this is 2, this is 3 and this is 4. So, if you have a 3,4 addition, then you will get a molecule like this. Now, there is another possibility of 1,4 addition. 1,4 addition. In this case, you get the product as this. Now, this polymer, every monomer unit can stay as a cis 1,4 polymer, which gives, we can write like this. Now, they can have a trans arrangement as well. This is a cis 1,4 addition, this is a trans 1,4 addition. Now, in the case of 1, 2 and 3, 4 addition, each this polymer chain also can have 3 possible tacticities. We will come in the discussion about tacticity in a minute, but for timing you take my word as that these polymers which have a stereocenter tertiary carbons, they can exist as 3 form: isotactic, syndiotactic and atactic. So, basically you can have 3 possible arrangement for this, same as here. So, you can now imagine how many possible isomers or isomeric form you can get by polymerization of this butadiene molecule, 1,3-butadiene molecule. Now, what is the difference between these two? This is a cis arrangement of the repeat units, whereas this is a trans arrangement of the repeat unit. Now, if you extend this polymer chain, you can write a cis structure like this. Now, every case, if you look the structure, you can write yourself, where for every repeat unit you have a cis arrangement. Here there is a cis arrangement, here there is a cis arrangement, and for this double bond also you have a cis arrangement. Now, if you look at these molecules, this is not very regular. As they are not very regular, what happens, they cannot pack well in a crystal lattice, and as a result this has soft polymer. So, it has a non-regular structure. So, do not crystallize. Hence, it is a soft material. Now, Tg for this is minus 73 C and Tm is 28 degree centigrade. Okay. Now, if you compare this to a trans arrangement where you can so, basically in this case every monomer unit has a trans arrangement. Now, you can yourself can imagine this is a very regular structure, which means if you have a regular structures, then the polymer chains can come closer to each other and pack very well. As a result, they can crystallize easily and hence the melting point is higher 74 degree centigrade compared to 28 degree centigrade. So, at a room temperature this has a crystalline structure. Crystalline domain exists in room temperature, which actually gives this polymer as a strength, and this is a hard material. So, this is a hard material, regular structure, crystallize easily. Now, how can you think of which one is a dominant product or which one is not a dominant product? So, what is the relative in a polymerization, what is the relative proportion of this all the possible structure we just discussed 1-3 1-4 addition, 3-4 addition and 1-4 addition. Obviously, between 1, 2, 3, 4 and 1-4 addition, between these three obviously it will be the addition which will gives the intermediate having lowest energy, obviously be a predominant product among these three, and most cases because the 1-4 addition gives a longer resonance stabilization, this is in most cases this is the preferred propagation mechanism compared to the other two. Now, between once you have a 1-4 addition between cis and trans, if you just consider what is the possible structure of the monomer itself. Now, you can think two type of spatial arrangement. One is transoid, where these two double bonds are in trans, and one is cisoid. Okay, now, the conformation or the configuration of the polymer chain will be determined by the conformation of the adding monomer, which the monomer which is getting added, the conformation of that monomer will determine the resulting polymer chain, and between these two the transoid structure is a much stable structure compared to a cisoid structure. So, yeah, unless there is a specific organization or specific mechanism occurring, in normal cases trans 1-4 will be a predominant product compared to a cis 1-4 product. Now, there could be isomerization among the intermediate states. Now, if I write so, this is a propagating chain end. Now, this can and this will take part in resonance, and it can form this is not, this is a chain end, this is not the polymer, this is a chain end. So, could be a radical, it could be a cation, or it could be a anion. This is the chain end, this monomer will come and add to this and the chain will propagate. Now, this single bond can be easily rotatable. Okay, it can be easily, we can rotate this around this single bond, and if we can rotate, we can get now when this in resonance, it will form this chain end. So, basically you can have one chain end with one active center, and because of resonating structures, it can actually form the another geometry around the double bond, and if now this propagates, it will form a trans polymer. If this chain polymer, this chain propagates, it will be a cis product. So, even if you have a cis chain end, it can isomerize and give you a trans product. Now, that depends upon the temperature. If your temperature is high, then there is this isomerization between these two monomer, these two structures are highly possible. So, there is a always almost equal possibility of this propagating and this propagating, which means that the resulting polymer will be a mixture of cis and trans product at higher temperature. If you lower the temperature, obviously this isomerization become less and less probable, then the most stable structure, which is a trans structure, will polymerize, which will product. Now, if you have a this R, depending on the size, obviously you can imagine if R is high, the more the size of R, the trans product will be more dominated, because the energy difference between a cis-wide and transformed will be much higher as you increase the size of the R. So, if you increase size of R in absence of any specific mechanism, the trans will be higher product, and if you increase the or decrease the temperature, again trans will be a higher or predominant product. Now, let us look at some data. If you take butadiene, this molecule which does not have any substitution, and isoprene which has a large substitution, then if you do a free radical reaction at 20 degree centigrade, you get the trans product higher. If you increase that size of that substitution from hydrogen to methyl, the size goes up. So, your trans product is become more dominating than or in comparison to the case where there was no substitution. Now, if you increase the temperature, compare between these two, isoprene free radical polymerization as 20 degree centigrade and isoprene free radical polymerization 100 degree centigrade. Obviously, as I explained in few minutes back, that if your temperature goes up, the isomerization, chances of isomerization or probability of isomerization will be higher. So, there will be always chances of cis and trans forming together. So, obviously, if you compare these two, now there is a significant increase in the cis isomer as well. Now, what happens in case of ionic polymerization of butadiene. So, let us again example of say isoprene. If we do in a non-polar medium and with a small counter ion, now we know in from our knowledge about anionic polymerization that the anion, the anionic chain length and the count, there is always a counter ion say M plus. Now, they can exist in different state. If the polarity of the medium is higher, then they will slowly move from a tight ion covalent bonding to tight ion pair, then to free ion pair. If the polarity of the medium is lower, then they will become closer and closer. If you are non-polar medium, they will become very tight ion pair. Now, if you are tight ion pair, then the smaller the size of this counter ion, the tighter would be your the interaction between the anionic part and the cationic part. So, in this case non-polar medium and lithium counter ion, they will be remaining as tight ion pair. Now, if you use this condition and make a polymerization of say conjugated diene, this counter ion lithium, so let us write here, will be very close, they are not isolated. So, if you add a when the new monomer adds, there will be a interaction coordination between the chain end, polymer chain end or active chain end, propagating chain end and the counter ion and the monomer like this. So, there will be a interaction between this positive counter ion and the negative propagating chain end and the new incoming monomer. As a result, now the cis, this is coming from same side. So, you will form product like so, this is a cis product. So, because there is a interaction between this counter ion and the chain end and the monomer, they will form a predominantly cis product. Now, if you increase the polarity of the medium, then obviously then the counter ion, in this case lithium, will be well separated, and if they are well separated, obviously there will be there will not be any possibility of such type of intermediate formation, and hence as usual the trans product will be predominant. So, if the medium is non-polar and your counter ion size is lower, then there will be a possibility of or there will be a intermediate formation by coordination between the anionic chain end and the incoming monomer, and that will lead to a cis monomer formation, whereas if you increase the polarity of the medium, then obviously the active chain N and the counter will be well separated, well solvated. So, they will be apart from each other, separated from each other. So, there will not be any possibility of this type of intermediate formation. So, as usual the trans product will be dominated. So, if you look at few datas, you take butadiene and isoprene, obviously we had compared anionic polymerization 20 degree centigrade in non-polar medium, hexane, anionic polymers at almost similar temperature at non-polar medium. Obviously, because there will be a dominated cis product in both the cases, the cis product is dominating. Okay. If you take or increase the polarity of the medium, if you compare these two, the temperature is almost close. If you instead of take a cyclohexane, you take diethyl ether, if you increase the polarity of the medium, keeping any other thing, then look at this, cis product is not that dominating now. Okay. If you increase the polarity further, then cis product will become lower and lower, increasing the polarity of the medium. Okay. Now, let us I think with this we have completed our discussion on conjugated monomer, polymerization of conjugated monomers. Now, let us talk about the tacticity. If you take a simple monosubstituted monomer, and then consider what happens when this polymerize. Now, we can consider a polymer where you can have two types of stereochemistry. You can have this, or you can have okay. So, this carbon atom where you have 4 different substitution. So, as we know from our knowledge, if carbon has 4 different substitution, then this is a stereo center or stereogenic center. Sometimes we also call this as asymmetric center, and it is a chiral also, it is a chiral center as well. Now, you can write, you can name whether it is R and S. Now, that will depend upon which get priority, whether this one or this one. Now, that will depend upon which is having higher length, whether there is a functional group or not. So, we do not know from this structure, we know whether this is R or S, but at least we know if this is R, then this will be S, or if this is S, it will be R. So, to avoid confusion, sometimes it is written at small r, lower case r, and sometimes it is written as S, and some cases or some people also prefer to write this is D L, or we know which is D or L, but if it is D and then is L, if it is L then it is D. Okay. So, these are the other type of nomenclature we use. Now, this is this cannot be, these two configuration cannot be interchanged by simple rotation of the around the single bond. Now, will that be optically active? By definition, this should be a chiral molecule. So, this should be optically active. Now, if you remember that optical activity is a very short range phenomena, and that depends only depends upon first maybe first one or two atoms or groups around this stereo center or asymmetric center. Now, in this case in a polymer there is hardly any difference between say first two group or atom in these two cases. Okay. So, basically though in true sense it is a stereo center and a chiral molecule, but because these two are long molecules and first few molecules are same, they are basically do not show any optical activity. So, they are basically achiral in nature. So, they do not show any optical activity. Now, if you can argue that the carbon which is almost at the end near to the end group, then obviously in end there will be some functional group and the other side will be the rest of the polymer chain. So, that carbon, that asymmetric carbon should have some optical activity. You are right saying that the carbon atoms, the tertiary carbon atoms at the end which has one of the functional group associated instead of a polymer chain, they should be chiral and show some activity, but their concentration in the polymer is so low that in practically they do not contribute any optical activity, or you do not see their contribution is so low that you do not see any optical activity when you get measure the optical activity of these type of polymers. Now, polymer also show optical activity if they are a optically active conformation. In a macro sense, if you polymer has a say helical structure or something like these biomacromolecules, then their conformational structure can have or cannot have any symmetry element which will result in the optical activity. Now, that happens in case of biomacromolecules where you have exclusively one such conformation present in the sample, but in case of synthetic polymers these conformations there are many conformation polymer conformations possible for single polymers, and in a polymer sample they averaged out and you do not see any effective optical activity for that optically active conformation. So, what if you add the next monomer, what would be the arrangement now? Now, it can have now two types of arrangement where I can have so basically in this case these two molecules, this two carbon atom has different configuration. Okay. If this is R, then it will be S, whereas in this case they have same configuration. If this is R, then it is also R. So, that is two possible. If you can add, if you think of adding another one, you can have another two possibilities and so. Now, if all these the configuration of this all these tertiary carbon atoms are same, then we call this is an isotactic polymerization. If this is all same, if you can think of that the next carbon also have same configuration, and if they are alternate, then they are this called syn diatactic this is isotactic, and if there is no order, then it is called atactic, which is basically random distribution of. So, if I can write this is D, 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 or say R, 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 whatever way you write, then this will be DL, 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 or RS, RS, RS type of configuration. This is alternate configuration of the carbons, symmetric centers, and in this case it will be arbitrarily. Atactic would be say D, D, L, D, L, L, D, something like that, whatever you, this is arbitrary, there is no order as such. Now, why you are interested knowing the syndactic tacticity of the chain polymers? Obviously, as you can expect from the structures, these two, both isotactic and syndactic, will have regular structures. Okay? They have regular structure. Obviously, isotactic will be having more regular than syndactic structure. So, if I consider a molecule like say propylene and make polypropylene out of this, then you can make a isotactic polymerization, isotactic, you can make a isotactic polymer of from propylene molecule, then isotactic polypropylene will having a regular structure will crystallize easily, and that will be hard molecule. And if you have a atactic polypropylene, then again there will not be any regularity in the chain. So, the chains will not be able to crystallize easily, and you will have a soft polypropylene, which is of no use in practical sense. So, if you want to have a application, practical application or utility of polypropylene molecules, then you should have a regular structures like isotactic, or some cases syndactic also able to crystallize, but probably in a lesser extent compared to a isotactic polypropylene. Now, we can have similar sort of tacticity in case of polymers where we do not have all carbon backbone. For example, if I do a ring opening polymerization of ethylene oxide, which we discussed in the last lecture. Now, you can imagine placing, let us consider propylene oxide. So on. So, here again you can have, if you have same configuration of these carbons, then it is like this is a same configuration. If you have same configuration for all the molecules, you will again have isotactic. If you have alternate configurations, then you have syndactic, and if their configurations are not any regular, they are arbitrarily placed, then you can again call this as a atactic polymers. Now, in this case, unlike polypropylene or other the carbon chain polymers, if you consider this carbon which is asymmetric nature, then in this case these two polymer residues, in this case this one and this one, they are actually different in nature. Unlike the polymers, chain polymers where only carbon backbone, in this case they are different, like in this case you have oxygen next atom, and in this case CH2 molecule. So, in this case you expect that this will show optical activity, unlike say molecule like polypropylene, and indeed they do show optical activity. This type of polymers actually show optical activity. Now, how do you synthesize? What are the ways you can synthesize? What are the strategies you can take to synthesize one particular stereoregular polymers like isostatic polymer or synergetic polymers? As you know by this time that it is always recommended or always beneficial to make or synthesize polymer having a definite stereoregularity, whether it is isotactic or stereotactic. They always are more helpful or more polymers which will have more utility compared to atactic polymers. Now, which one of these three possible stereo arrangement which will be dominated, that again determined by the medium where you are doing, and of course the mechanism, the initiation mechanism, where is the cationic mechanism or the radical mechanism you have taken. For example, if I consider case that is the terminal carbon atom which is the active center. Let us consider this is a propagating chain, whether this is a active center. Now, it could be a radical, it could be anionic, or it could be cationic. Of course, if you have a cationic, then you have a anionic counterion. If you have a anionic, then you have a cationic counterion. Now, what is the geometry of this carbon atom? What is the hybridization? If this is a radical, then obviously this is sp2. If it is carbocation, then also it is sp2 and it is a carbanion. Then ideally it should be sp3, but because you have a substituted group, substitution here R. Now, we know this, the monomers which undergo anionic polymerization, they actually get stabilized by resonance with this substitution. If you remember acrylonitrile or methyl methacrylate, where this anion charge get delocalized by resonance with the substituted group, and that requirement, this requirement of resonance with the substituted group again makes this as planar. So, this is actually, this carbon is having a planar structure irrespective of sp2 is whether it is a radical carbocation or a carbanion. Now, that will change if your counter ions are very tightly bound with the carbon atoms. If you have an anionic group and a carbanion, and if your counter is tightly bound, so if you have lithium plus you are doing a reaction with n-butyl lithium in a non-polar medium, then this carbanion C minus will be having very strong tight ion pair, as we discussed in case of that conjugated diene polymerization, they will be very tight. Now, in this case, this will not be a planar, this carbon will not have a planar geometry. Okay. So, first let us discuss where either you have a radical or you have a cation, carbocation or a carbanion, where the counter ions are free, they are not tightly bound, and if they are free, that happens in a polar medium, then as we discussed now, you can consider this carbon, the terminal carbon, as a planar molecule. Okay. It has a planar geometry. Now, if here it is a planar geometry, when the next monomer comes in, because it is a planar, it can come from both the sides. So, there is no special, it can come for this or it can come for this side as well. So, no special preference of or hindrance from one of the other sides. Let wipe it off to avoid confusion, this one. So, in general case, if you are talking about radical polymerization of or ionic polymerization, where you have the counter ions are free, then the stereochemistry of this carbon atom will be determined once the next monomer gets in. So, what happened, CH2 okay. This is the monomer which I have written here at the end now. So, what happened for this, the configuration of this carbon, which side now the hydrogen and R will come? Obviously, they will prefer, because R is up. So, now R will prefer to be a down and hydrogen will prefer to have a to avoid the steric hindrance. Okay. So, unless there is a specific mechanism, in normal case there will always be syn diatactic would be a preferred tacticity. Now, again this bond they can freely rotate. So, obviously, if the temperature is higher, then it can rotate and form the isotactic polymer as well, okay, isotactic linkage. And in that case, if there is random orientation of two carbon atom, asymmetric carbon atom, then you are going to get a syn diatactic atactic molecule. So, if you decrease the temperature, you are going to increase the concentration, the tendency of syn diatactic formation, and if you increase the temperature, then there will be the preference will be lost. So, we can write these two approaches when two rate constant, when Kr and Km, where Kr is the rate constant for the syn diatactic addition, R means racemic to consecutive carbon, they will have different configurations. So, we are writing Kr and Km for the meso, which will give the isotactic addition. This is syn diatactic addition. Now, their ratio will determine which product gets dominated, and that will get determined by the difference in the Gibbs activation Gibbs free energy between the two molecule, where we can write like this. Where this del L star and del H star is the difference in the activation energy, difference in the activation entropy, and this is the difference in the activation energy between the two routes. One is interacting acidic formation, and from experiment data we get this around -4 to -8 kilojoule per mole, and this we get around 0 to 4 joule per mole. So, this is very low. So, the preference 1 after 1 over 1 would be determined by the difference in their activation energies, and if you increase the temperature there will be no preference between these two, and hence there is a tendency for any of the two stereo regularity formation which will lead to attractive molecule attractive polymer. If you reduce the temperature, obviously there will be increased tendency of syn-dialectic polymer formation. So, if we increase the temperature, then we will get more of a syn-dialectic polymers. And again this we are talking about where you have either we are talking about a radical polymerization or an anionic or cationic polymerization, where we are carrying out the polymerization in a polar medium, where you have the counter ion and the active centers they are free, as they are exist as a free ion. Now, what we will do in the next lecture, we will discuss the strategy how we can and how this ionic polymerization can or would give the isotactic polymerization. As you have seen that with decrease in temperature we get preferentially syn-dialectic formation, and if we increase the temperature we get attractic formation. So, how to get isotactic polymerization, isotactic polymers, we will discuss that in the next lecture.